Hello everyone. Okay. Um so hello to everyone here. Um Today we're going to be doing a bit of probability. Um I know that oftentimes probability can sometimes be one of the most challenging units for math methods. So I'll be going through it today. I won't be going through all the basics, and I'll just go through some sample questions for you, and I'll go through my thinking process because I think that's the most important part of probability, the way that you get to your answers. So I'll start in a little bit. Just give me one sec. Okay, so we'll start. So this question is from the 2019 exam, and I'll give me a sec. I'll make a start on this. So, straight away from this type of probability, I can see that it's a probability density function, and straight away I'm thinking the area under the graph, right? Because to obtain the probability of a certain variable from a given domain, you got to take the area under the graph of a probability density function. And for this question, we're asked to find the mean lifespan, and of course, you just got to know the formula to find the mean lifespan, which is just e to the x is equal to the integral of your function over its maximal domain times by x. So I get this, and then it's an exam 2 question, so I can just do this on my CAS. First off, I'm gonna define my function. So I get I define my function, and then I can integrate. Oh fuck. Here we go. And then I can integrate times it by x, and that should give me the expected value. So my expected value is 10 over 3. There's not much to that question. It's just you got to know the formula for to find the mean of a probability density function. So moving on, question B: in a sample of 80 Lorenz birdwing butterflies, how many butterflies are expected to live longer than 2 weeks? Correct to the nearest integer. So again, I think back to area under the graph in a given domain, and in this one, it asks me how many butterflies are expected to live longer than 2 weeks, and my variable x here gives the number of weeks that a butterfly will live. So to find the probability, I would just take the area under the graph from 5 to 2, because that's saying the probability of finding a butterfly that would live from 2 weeks to 5 weeks. And I would integrate over my domain. And on the CAS, that would give me oh so I don't know how to convert from fraction to decimal on the computer CAS, so I'm just gonna do it on the calculator I have on me right now. Okay, so you get that fraction, but the question asks you to the nearest integers. So obviously you want to convert to you want to convert to. Oh, I'm sorry. Okay, I've misinterpreted the question, and it's not asking for the probability of butterflies that are expected to live longer than 2 weeks, but it's how many. So, so I'd get the probability first off, which is 2853 over 3125. And then since that's the probability of finding a butterfly that would live longer than 2 weeks, I would just times that by my total number of butterflies to find the expected number of butterflies that would live longer than 2 weeks. So timesing that by 80, I get 73 butterflies. Okay, I think that's pretty straightforward as well. Moving on, question C. Finding the probability that a Lorenz birdwing butterfly lives for at least 4 weeks, given that it lives for at least 2 weeks, correct to 4 decimal places. So I'm thinking back to the stuff we learned in year 10 probability, especially the formula for A given B. So I'm just going to write it out here, that it lives for at least 4 weeks. So it's x is greater than or including 4, given that it lives for at least 2 weeks. And of course, we can write this formula out as PR x is greater than 2 intersection x is greater than 4 over PR x is greater than or equal to 2. So we can simplify this, the top probability first of all, because if you think about it, the intersection of x is greater than or equal to 2 and the intersection of x is greater than or equal to 4, it's basically saying all the numbers that are greater than or equal to 2 whilst also being greater than or equal to 4. And of course, logically, it's just all the numbers that are greater than or equal to 4, because you can't have 2 or 3 because they aren't greater than or equal to 4. So we get PR x is greater than or equal to 4 over PR x is greater than or equal to 2. And then of course, from the CAS, you would integrate over that domain. So I would get just integrating from 4 to 5 f of x dx, 821 over 3125. So I get 821 over 3125 divided by 3125 over 2853, which is my previous probability for 2, but we already figured that out. So let me do this here. And I end up with a probability of 821 over 2853. And then when I approximate that, that should equal to 0.28784 decimal places. So, there's no questions right now, so I'll just keep moving. Next question, question D. The wingspans of Lorenz birdwing butterflies in town A are normally distributed with a mean of 14.1 centimeters and a standard deviation of 2.1. So now I'm noticing that I'm moving on from I've moved on from probability density functions to the normal distribution. So let me just write this out real quick. Let's let W equal wingspan, and that's normally distributed with a mean of 14.1 and a standard deviation of 2.1, just for clarity. So first question is asking us to find the probability that it is between 16 and 18. So straight away I will just put that into my calculator. There's nothing much to it. Using the normal CDF, lower bound 16, upper bound 18, mean 14.1, and standard deviation of 2.1, and I get an answer of 0.1512, rounding to 4 decimal places, of course. Moving on. Question E. A Lorenz birdwing butterfly is considered to be very small if its wingspan is in the smallest 5% of all the Lorenz birdwing butterflies in town A. So, find the greatest possible wingspan in centimeters for a very small Lorenz birdwing butterfly in town A. So this is whenever you see in a normal distribution question, whenever you see a percentage or a given area, you know to use the inverse normal, because we know that the inverse normal gives us the area from a graph to a specific point. So let's say it gives you an area of 5%. You know that PR x is smaller than A is equal to 0.05. So from this question, it's going to be very small if its wingspan is in the smallest 5%. So the smallest 5% would be this area. And find the greatest possible wingspan. So it's basically asking you, find the point where 5% of where the smallest 5% of butterflies is. So find this point here. Find point A. And then that's just an inverse normal question. So I'd use my calculator. Inverse normal. The area is 0.05 and the mean is 14.1, standard deviation 2.1. And of course, this question we don't have to, but remember to always take the inverse normal from the left tail. Say if it was PR x is greater than A is equal to 0.05, then you would have to rearrange to make PR x smaller than A is equal to 0.95. But this question we don't have it, so I'll just click enter. And we get an answer of 10.6458. So conceptually what that means is at where the wingspan equals to 10.6458, you have 5% of the smallest butterflies. You have 5% of the butterflies. You have 5% of all the butterflies with the smallest wings. So the largest should be 10 point, correct to 1 decimal place, 10.6 cm. Okay. No questions still. Guys, remember, feel free to ask any questions in the chat. I will happily answer them. Okay. Question F. Each year, a detailed study is conducted on a random sample of 36. It's considered very large if its wingspan is greater than, and the probability that any Lorenz wing butterfly in town A is greater than 17.55 is that. So straight away, I'm thinking of binomial distribution, because the binomial distribution involves a sample number or number of trials, which is 36. It involves a probability of success, which is in this question 0.0527, and then it also involves, you have one set outcome. You have either a fail or a success, and in this question we do. So the one success is it's very large. If something's not very large, then it's just a fail. So I'll just write this out for clarity. W wingspan is binomially distributed with a trial number of 36 and a probability of success of being 0.527. So with that in mind, we can do question FI of finding the probability that 3 or more of the butterflies in a random sample of 36 are very large. So we're given that the probability of it being very large is 0.0527. So it's just as simple as setting it out like this. Make sure it's inclusive because you're finding 3 or more of the butterflies, and just doing that on the calculator. So menu 5, binomial CDF, number of trials 36, probability of 6, 0.0527. And make sure, because on the CAS calculator, when you're entering the lower and upper bound on the CAS calculator, it is inclusive. So say it was probability of W greater than 3, not including 3, then you would have to enter the lower bound as 4, because in the calculator, if you enter 3, it will include 3, and then your answer will be wrong. But in this question, it's including 3, so we can just enter 3. And then of course the upper bound is 36, because you have 36 butterflies, so you can only ever have at most 36 successes. So just press enter, and the probability there gives us 0.29469, so I round up to 47. Okay, moving on to question II. So finding the probability that n or more butterflies in a random sample of 36 Lorenz birdwing butterflies from town A are very large is less than 1%. So, when you're given in a question n, or when you find yourself faced with the words like find the smallest value of n, find the smallest population size, you know that it's a question involving finding the sample size from a given probability. So setting this up here, we're trying to find the probability that in a random sample of 36 Lorentzian butterflies, so the number of them that are very large is less than 1%. So so it's basically saying that the proportion will be less than, not including, just less than 0.01. My bad. So of course, when you're faced with a proportion, and when you're faced with a proportion, and you've previously been answering a binomial distribution question, straight away you should be looking to convert this proportion into an x value. So what I mean by that is, because I have 36 butterflies and 1% of them should be 0.01 is equal to times by 36. Hang on. Okay, so you want to times it by in a random sample a very large is less than 1%. Okay, so you want to times 36 by 0.01 to find the actual number of butterflies that you want. To find the actual number of butterflies that you want. So we end up with 0.36 butterflies. And I'm sorry guys, give me some time to think, because whenever you do this proportion, you should be getting an integer, because binomial probability, you can't have decimals, you can't have successes in between numbers. So okay, so I've misinterpreted the question again, and the question is basically asking us find the probability that n or more butterflies in a random sample of 36 or very large is less than 1%. So find the probability that the wingspan is greater than or equal to n is equal to or is less than 0.01. So where n is our number of successes. So for a question like this, we actually need to use our formula for binomial distribution so we can clearly see where the variables are going. So I'll just lay it out right here, remembering that the formula for binomial distribution is nx px times 1 minus p to the n minus x, where x is the number of successes. So in this case, I'll use a different variable for x because we have n, so I'll just put in n. So we would lay it out like 36 n p to the, p is 0.0527 from here. That's the probability of success. So times it by n, which is the successes we want, and times that by 1 minus p. Oh, my bad again. We're given p, so 1 minus and times it by 36 minus n, and all that has to be less than or equal to or less than 0.01. And so inputting this into the calculator won't work because this right here involves taking the factorial of n dash, and of course if you don't know what n is, then you'll never know what the factorial of n dash is, because when you're trying to find the factorial of n dash, you're trying to find n times n minus 1 times n minus 2, etc., all the way to whatever n is. And of course that won't work because you don't know what n is. So how can you find what n minus 1 is and what n minus 2 is? So instead we would set up there's a special way to do these questions. You'd have to set up a function for the binomial distribution of f of x, and what this would look like is, so I'd define a function. So just bear with me, I'll explain in the end. So I'd define a function of f of x as equal to binomial CDF So 36 is our number of trials. 0.0527 is our probability of success, and our variable that we don't know is n. So the number of successes that we want. So I put in x here because I've defined f of x in terms of x. So instead of n, I'll use x. And then of course the maximum number of successes is 36. So I define that, and then I would add a spreadsheet. Give me a second. I'd add a spreadsheet, and then I would change this spreadsheet into a table, and then I'd select my function f of x. So I know that seemed very unclear, but you don't need to know like the meaning behind why you do this. It's just that when you're faced with a binomial distribution function where you have an unknown that you can't work out for, just define it as a function of f of x with x as the unknown, and then input it into a graphs or spreadsheets, and then switch it into a menu, and then you can see. So we're looking for the greatest number of n where the probability is smaller than 0.01. So I can scroll through here. Here we have probability 0.0857. And as soon as I reach a probability of less than 0.01, which is here, I would get my answer. So at x or n is equal to 7, my probability is less than 0.01. So my answer is n is equal to 7. So, guys, I know that was quite confusing, so post any questions you have about the explanation in chat. For these types of questions where you have an unknown in this part, in the factorial part, in the combinatorics part, you have to set up an f of x defining the binomial CDF of f of x. Yes. I'm just looking at questions right now. If anyone has a question, please ask. Please do ask. Oh, okay. So how did I put f of x in the table? Of course. So let me just delete everything, and I'll just show you again because I don't really know how to go back. Okay. So I'd first define my f of x is equal to binomial CDF 36 0.0527 with x as my unknown, with x as my lower bound, because that's what right there, that's where the lower bound goes, and my lower bound is unknown, so x is my lower bound and 36 is my upper bound. So I define that as f of x, and concerning how I put f of x into the table, so I have my table right here. So on the CAS calculator, on the handheld, it'd look like you press menu on the spreadsheet, and then you press 5 and you press switch to table, and then as soon as you press switch to table, this little thing should pop up, and then just click that and you get f of x. So is that clear? I love maths 69. Okay, and then of course scroll through until you find the first value where your probability is given, and of course here it's 7, so n is equal to 7. Okay, so I hope that helped, and we're gonna move on. Right. Oh, I think my OneNote is frozen. Okay, so we're gonna move on. Question FIII. So for random samples of 36 butterflies in town A, p hat is a random variable that represents the proportion of butterflies that are very large. Find the expected value in standard deviation of p hat, correct to 4 decimal places. So this question, straight away, I'd be thinking of the sample proportion formula. Thinking back to my theory of how, in a very large population, which this, or not a very large, just in a large population, which this is, the sample proportion is just equal to the proportion of, the population. And of course, our population proportion is equal to 0.0527, which is given in the question. And I'd also sync to my standard deviation of my sample proportion, which is this formula right here. where the bottom is equal to n. That is just p. Okay, so I'll try and explain the theory behind this a bit further. So when you're finding p hat, you can think of p hat as a whole nother variable with a different mean and a different standard deviation, because when you take a sample, the mean won't always be the same as the population mean, and the standard deviation won't always be the same as the standard deviation of the population. So you want to find a whole new p hat standard deviation and a whole new p hat mean. But there's a rule in math saying that if you have a large population of 36. Oh, and by the way, to find a large population, NP must always be greater than 5, where N is equal to population number, and P is equal to probability of success. And NP is always greater than 5, which this is greater than 5. So that is how it goes. Finding the proportion like this and finding the standard deviation using this formula. And I'll just sub that into my formula, which is square root 0.0527, 1 minus 0.0527, and that over 6. So our expected value of p hat is 0.0527, and our standard deviation is, oh, not that, and our standard deviation is 0.0372. So, are there any questions regarding how I did question FIII, getting the expected value and standard deviation of p hat? Actually, I'm not sure if the standard deviation formula is. Let me just search it up real quick. Yes, this is being recorded, so I'll upload the VOD to my YouTube so you guys can watch it. Here, Gus, I'm just gonna look for you real quick if it's on the formula sheet. And yes, it is. Here we go. Standard deviation of p hat is p1 minus p over n. Here you go. So it is on the data book. So don't worry about memorizing it. Just know that it is on, and you can look for it in the data book. So, moving on. Question FIV. So what is the probability that a sample portion of butterflies that is very large lies within one standard deviation of 0.0527? Correct to 4 decimal places. Do not use a normal approximation. Okay. So from the question here, straight away you want to. So when faced with very large word questions like this, you want to just try and lay it out. Like just try and convert all that chunk of text that you're faced with into some mathematical symbols that you know how to work with. If there's anything to take away from that, just set out all your things that you know first of all. So a sample proportion of butterflies that lies within one standard deviation of 0.0527. So that's kind of asking, because we know that our standard deviation is equal to that. So that's kind of asking that, sample proportion that lies within 0.0527 plus 0.0372, because that's one standard deviation, and that lies between, hang on, let me just do this, and more in the middle. Okay, so because we know that one standard deviation is this, and we know that our sample proportion is this, we can write out our question like this, because it lies within one standard deviation. So it should lie within 0.0527 plus 0.0372, and it should lie within 0.0527 minus 0.0372. And of course, when you do all that subtraction, you'll get, just doing that on my CAS right now, you get PR 0.0155 is smaller than p hat, which is smaller than 0.0899. Okay, so now you're left with this, I guess, it can be quite daunting. You know, when you're looking at a sample proportion thing, it can seem quite unfamiliar. But whenever you see a sample proportion, if there's anything to take away from this lesson, whenever you see a sample proportion, always convert it into its actual x value when the question says do not use a normal approximation. And I'll explain this later, but right now the key thing to take away, if anything, from this stream, is always convert these values into their actual x values. And what I mean by that is, so if you think about it, a proportion of 0.0155 is basically saying that, you know, 0.0155 of the entire population is a specific trait. So, from our random samples, so that means that the actual number of butterflies in a proportion of 0.0155 is equal to 0.036. And of course, you need a whole number. You need a whole number of x because you can't have 0.036 butterflies. So you just round that down to 0. And then, of course, with a proportion of 0.0899, the same thing applies. You want to convert that to the actual x value, the actual number of butterflies that are very large. So times that by 0. Actually, let me just do this again real quick. So I kind of just rounded out the last one, but I'll just do that exactly so it's more clear. So 0.155 times 36 equals to... Oh, okay, and there was my mistake. So that actually is 0.558, so you can round that up to 1. So the actual x value of butterflies that are large with a proportion of 0.0155 is 1. And we do the same thing for the proportion of butterflies with 0.0899. Just times that by 36. Should equal to... that should equal to... Oh, why is that there? Okay. That should equal to 3.23, which you can just round down to 3 because you can't have 3.23 butterflies. So, once you have that, you know, go back to the question, go back to what it's asking. So it wants to find the probability of the proportion lying between these 2 points. So we can rewrite that as PR1 is smaller than X, which is smaller than 3. Lies within 1% deviation. Oh, and of course you would use including now, because as you can see, like from a portion of 0.0155, you get 0.558. So on a number line, that would look something like this. So like, let's say 1's there, 0.0558 is there. So if you're trying to find everything that's bigger than that, then one is bigger than that, and 1 is also within that range. So you would convert that now to a including. And the same goes with 3. Like, you're trying to find everything smaller than 3.23. When you round it down to 3, 3 is included within that range. So you'd end up with the probability of 1 is smaller than X, which is smaller than 3. And then we notice that looks just like our binomial distribution, where the n is equal to 36, the p is equal to 0.0527. So I just put that into my calculator. Number of trials 36, probability 0.052, lower bound 1, up bound 3, and I get my probability is equal to 0.4276, and that's your answer. So key thing to take away from this question. So that was a lot of me just doing the question, and so the key thing to take away from this question, obviously, or not obviously, or just, you know, if you haven't listened to me the entire time, just the key thing is when you see a proportion question where it's like greater than, equal to, or greater than and less than, always convert it to its actual x value and then use the binomial distribution. Let's write that down here. Convert to x value, use binomial CDF to solve. Okay. And that just does it. That's just about does it for the question from 2019. And now I'll be going through another exam 2 question from the exam 2018, which is also probability, and it has some different types of probability in it, and it will be helpful to just go through to broaden your, I guess, your knowledge of probability. Oh, okay. So here I've gotten a question from Iconic Supremacy. Thank you very much. So how do you convert it? Lol. Okay. Great. That's a great question. I'll answer that. So, in this question, I'll just use the example in this question. So you have a proportion of 0.0155 and a proportion of 0.0899. So if you think about it, that's saying that in a population of 36, a proportion of 0.0155 of them are very large. So converting that to percents, 1.55% of them are very large, if that makes more sense in your head. And of course, when we want to find the actual number of something from a percentage, we times the percentage by the actual number. So converting from proportion to the x value, you just times by the population number is equal to the x value. So if you didn't get any of what I said, just learn this. To get the x value, times the proportion by the n value, or by the proportion, by the population. Okay. So that's how you convert to the x value. So let me just reiterate, this is really important because, this type of question of a proportion being larger than or less than something will always, I guarantee you, will pop up in an exam too. And just remember, convert the proportion to an x value and then use the binomial distribution to calculate. So just keep that in your heads. That is very important. Okay, moving on to question 4 from exam 2018 now. So, alright, just having a read of the question. Doctors are studying the resting heart rate of adults in 2 neighboring towns, Mathsland and Statsville. Resting heart rate is measured in BPM. Okay, so filtering out all this useless information. We know that normally distributed, mean of 68, standard deviation of 8. So, probability that a randomly selected masculine adult has a resting heart rate between 60 and 90. So straight away, I know that it's normal, so I use the normal CDF. Menu 552 for those of you who've forgotten. And lower bound 60, up bound 90. Mean is 68, 8. So that was a very straightforward question. It's really a free mark. Just know how to use your calculator. And again, menu 552 to get normal CDF. Okay, moving on. So a person's heart rate is slow if it's less than 60. So writing that out in math terminology, probability that the probability that a randomly chosen adult has a slow heart rate is 0. So PR x is smaller than 60 is equal to 0.1587. Let's just write that out. It is known that 29% of Mathsland's adults play sports regularly. It is also known that 9% of Mathsland's adults play sport regularly and have a slow heart rate. Right, so I'm given a bunch of these percentages, and usually when you're given a bunch of percentages, you can probably set out a Karnaugh table, and if you don't know what that is, I'll just draw it for you. So you probably know what this looks like. And you use this when you have 2 variables. When you have, I'll just use A and B. And you can have an event being A or A and A not B. And you can also have an event being B and B and not B. So A and A complement and B complement. So in this case, our variables are H and S. So just write them out. H dash. And again, I'm just going to reiterate. Use the Karnaugh table when you can see that you have 2 set variables that can either be that can either have an event of being A or not A, or B and not B. If that's clear. Okay, so setting up the table, I know that 0.29% of 0.29 of them play sport regularly, so S is equal to 0.29. H is the event that a randomly selected Mathsland adult has a slow heart rate. And obviously I've obtained this from here. PRX is smaller than 60 is equal to this, so H is equal to 0.1587. And obviously all my probabilities will add up to 1, so I can deduce from that this and this, so just do 1 minus. That would equal to 0.8413, and the other probability is 0.71. And from that we can determine the squares inside of the table. So it is known that, and here is the information that it is known that 9% of mathlons adults play sport regularly and have a slow heart rate. So it's saying that 9% of them are in S and H, so S and H, and that is 0.09. And from that you can fill out the rest of the table. 0.2. Let me just work these out. So that is, that is 0.0687, and that is 0.6413. Sorry if that's a bit small, but you obviously won't need to use all those values. I've just set it out for a bit more clarity. And then here, so find probability H given S. So thinking back to our given probability formula, that's the same as saying H and S over P heart S. And because we've laid out our table, it becomes really easy. We can see that H and S is 0.09, and PRS is equal to 0.29. And then just do that in your calculator, and you get 0.310 to 3 decimal places. And now, justify if the events H and S are independent. So, there is a formula for this. So, for events to be independent, then the PR of one times the PR of another has to equal PR H and S. So you just sub into this formula and check if it's right. So H times S is 0.1587 times 0.29, and that should equal to 0.09 if it's independent, but if it's not, then it's not independent. And that is equal to 0.046. 0.046 does not equal to 0.09, therefore not independent. So again, the key formula there is if events are independent, one event times another event will equal to the intersection of both events. Yes, Gus is right. It's a super quick and super easy 1 mark question. Alright, moving on to question CI. Find the probability that a random sample of 16 Mathsland adults will contain exactly one person with a slow heart rate. So I'm thinking binomial probability instantly because I'm given a sample size, I'm given the number of trials, and the p is also known because I calculated the p before, and the probability here is for slow heart rate, and obviously slow heart rate is 0.1587. So P is equal to 0.1587. So in exams, the questions will be a lot like this, where the probability carries over from one question to another. So just remember to read the question carefully, filter out all the useless information, and obtain the useful ones. So here, I remembered that the probability was 0.1587, so I put it back into this question. Just remember, Gus asking for a proof of 0.046 not equaling 0.09. Okay. The calculator should say false, and there we go. There is your proof. So, continuing with this question. So P is equal to 0.n is equal to 16, and the probability that will contain exactly one person. So I think this is quite straightforward, easy 2 marker. PR x is equal to 2. Oh, sorry. Your H is slow, so it should be H is equal to 2. Want to be careful just in case VCAR wants you to have the correct variable. So H is equal to 2. And then using the binomial PDF, remembering that you use PDF for a single value, you use CDF for multiple values. So menu 55A, I'll just write this out for the video. So menu 55A, number of trials is 16, probability of success is 0.1587. and the x value is 2. And in my calculator, oh sorry, I was doing that on my handheld. I should probably do that on here. So binomial CDF 16 0.1587 2, and our answer is 0.2689. Okay, and moving on to II. So p hat is a random variable that represents the proportion of people who have a slow heart rate. Find the probability that the proportion is greater than 10%. So this is perfect. This is exactly what I was teaching you guys before. It's a binomial distribution question. You have a p hat, so instantly convert this into an x value. Oh, I'll just lay out the question real quick. So it's trying to find that p hat is greater than 10%, so it's greater than 0.1, converting to decimals. And obviously convert 0.01 to x value. So you do 0.1 times 16 is equal to 1.6, which is equal to 2, because you want to round up, because you can't have a decimal value for, you can't have 1.6 of a person, so you round up to 2. So that means that the probability of p hat, I'll make that clearer. That means that the probability of p hat greater than 0.1 is the same as the probability of x being greater than or equal to 2. And of course, you're including 2 because 2 is a part of the domain of 1.6 to 216. 2 for all numbers greater than 1.6, you include 2. So that's why we use x is greater than or equal to 2 inclusive. And then you just use the binomial distribution. N is equal to 16. P is equal to 0.1587, because that's a probability of success for slow heart rate. So on the calculator, binom, damn it. On the calculator, binom CDF 16 0.1587 2. Remember your calculator does this inclusively, so I'm entering 2, and 16, which is our max. So the answer is 0.7469. Alright, moving on. For random samples of n Mathsland adults, Pn is a random variable that represents the proportion of people who have a slow heart rate. So, and it gives you this kind of very scary looking equation here, and I actually think this is quite a hard question because you need to be able to really think this through to understand it. So I'll go through it now. So the probability of n, of the proportion of n, so this is saying that you don't know n is greater than 1 over n, is greater than 0.99. So when you're faced with, oh sorry, Gus, I didn't see your question until now. Yes, it should be h. My bad. I think I wrote that as a silent question, but you guys get the picture. And that was just me making a mistake here, but make sure to use the variable that VCAR wants you to use. Alright, continuing. So for this question, it's best to try and sound it out in your head, if that makes sense. So really try and understand what the question is asking. So the question is asking the proportion, the question is asking for the total population size, for the proportion to be greater than 1 over the population is greater than 0.99. So if you think about it, if our n value is our population, and you're trying to get, and the proportion is 1 over the population, doesn't it make sense that your x value is 1? Because if you're dividing 1 by the population, you get the proportion. So the reverse is true. Your x value is 1 because when you find the proportion of something, you're dividing the actual thing by the population thing. So look, the reverse applies here also. So p hat is equal to x on n. Therefore that n p hat is equal to x. And of course, we are given x, which is equal to 1. So x is equal to 1. So our our x value, which we just figured out, is 1. Picture has not been gotten. I'm not sure what that question means, Gus. So, if you want to ask a better question, do so. But so the x value is equal to 1 because we've just sounded out that p hat is equal to x over n, and it's given to us that x equals 1. So x is equal to 1. So then it becomes just another simple binomial distribution question. So PR x is greater than 1 is greater than 0.99. And here is when we would use our knowledge of finding the sample size to determine n, because from this, n is unknown. Right? So we'd set up an equation to do it. And to make things easier on us, like just think about what this thing is saying. So probability x is greater than 1 is greater than 0.99. It's saying that the probability from like everything above 1 to n is greater than 0.99, and you have to find n. So that'd be impossible to do because you can't do n factorial of, let's say, 5, 6, 7 because you don't know what n is. So instead we can express this equation like this, because PR x is greater than 1 is all the values that are more than 1. So 2, 3, 4. But so the values that it's excluding is PR x is equal to 0 and PR x is equal to 1, because it's not inclusive, it's not including equals to 1. And since that is equal to, or since that is above 0.99, we can say that PR x is equal to 0 plus PR x is equal to 1 is lower than 0.01. And then, or equals to 0.01, sorry, because when you're solving a calculator, you can't do this inequality really. You got to set it equal to 0.01. So then you'd lay out. Oh, okay, Gus. Thank you for your input. But moving on. So, and then is where you can use your binomial distribution formula. So, my pen keeps on disappearing. Oh, here it is. Oh my god. Okay, sorry, I'm just getting my pen back. Okay, so then we use our binomial distribution formula. So n to the 0 times by p to the 0. P is, we know p from carrying across from last question, which is 0.587 to the 0 times 1 minus p to the n minus 0. I'm going to have to go a bit across here. Plus n1 times 0.1587 to the 1 times 1 minus 0.1587 to the n minus 1 is equal to 0.01. Okay. So, if you have any questions on how I've done that, please ask. But when you're given, or when you're trying to find the sample size, like you gotta be careful for the vocabulary here. So when it's asking for, the lowest or greatest value of n, you always want to be using the binomial distribution formula. So again, if there's anything to take from this, when you spot questions asking you for the lowest or maximum value of n given a probability, use the binomial distribution formula and set it out. Set it out in a way that's possible. So I changed that from greater than 1 to just PR x is equal to 0 plus PR x is equal to 1. So doing this, we know that n to the 0 just simplifies to 1 times 1, so everything there disappears. So let me just work out 1 minus 0.1587, which is, oh shit, I need to get my pen back. So that is 0.8413 to the n plus, so this is asking how many ways can we take 1 from n, so n times 0.1587 times 0.8413 to the n minus 1 is equal to 0.01. Okay. And then we would solve for this on the calculator. So I'm just going to enter that in now. To the n plus to the 1, or to the 1 is already cancelled out, times 0.8413 Oh, I forgot to put in solve for n. And then we get n is either equal to negative, but we know like you can't have a negative population, so straight away we take that out. And n is equal to 38.9253. But you have to be careful here because 38.9253 is decimal, and then you can't have a decimal population, right? You can't have a decimal of a person. So originally you're trying to find the, hold on, bear with me. So you're trying to find the least value of n for which the proportion is bigger than 0.99. So and here, when we let it equal to 0.01, it was really just for the ease of solving this. We're trying to actually find n such that it's lower than 0.01. And because of this lower symbol here, we can actually round that down. Because if you think about it, if you round up, you're exceeding the minimum probability. But if you're rounding down, you're staying within the limits. And just so it looks clearer, I can graph this for you. And of course, if you like are struggling with the conceptual understanding, graph it, because that n equation, it is an equation that you can graph, and then you can clearly see where it's less than 0.01. So 0.8413 to the x. Okay, and then here I'm trying to find the point where it's less than 0.01. So I need to analyze, I need to trace this real quick. Just moving along, looking at the y value, trying to find the first bit where it's less than 0.01 and it's an integer. So this is for if you're having trouble to figuring out if you should round up or down. So here we're approached with 0.01, and then, oh, okay, my bad then. So you actually rounded up in this case. So I think that's a perfect example of why you should use the graph to just, make sure to round correctly either up or down, so you don't make a mistake in your rounding. So n is equal to 39, not 38, because from the graph we can see that the first integer point where y is equal or less than 0.01 is 39. Oh, actually, in fact, we can go even further, because our original one was less than 0.01, so it's not including 0.01. So from our graph, if we go up, 39.3 is the first point where it's less than 0.01, but 39 is equal to. So, in fact, this statement is untrue, because at n is equal to 39, the probability is still 0.01, so n would have to equal to 40, because 40 is the point at which n is equal to 40 is the point at which the probability first dips below 0.09. Like 40 is the first integer. So that does it for finding sample size. And if that was quite confusing, you guys can always ask me. Just ask in the chat for me to clarify something, for me to clarify anything. So moving on. We're nearly done. We just have a bit more. Okay. So Question DI. The doctors took a large random sample of adults from the population of Statsville and calculated an approximate 95% confidence interval for the proportion of Statsville adults who have a slow heart rate. The confidence interval they obtained was 0.102, 0.145. So I think this is again an easy one marker, because if you remember, the formula to calculate a confidence interval is just this, where like when you plus or minus, you get these two. So if you think about it, your proportion should be in the middle of those two. So, and to find the middle value, this goes back to like year 8, year 9 maths. You just add them together and you divide by 2. So p hat is equal to 0.102 plus 0.145 divided by 2. On the calculator, so the sample proportion is 0.1235. Okay. And the explain why this confidence interval suggests that the proportion of adults with a slow heart rate in Statsville could be different from the population in Mathsland. Let's just go back and read what we know about Mathsland. Okay, so Statsville adults who have a slow heart rate is the proportion is 0.1235. So we know that. And the proportion of adults who have a slow heart rate in this one is 0.1587. So because, straight off the bat, p hat is different. Therefore, calculations will be different. And you can clearly see, like, with a different p hat variable, you're going to get a way different standard deviation and thus a way different confidence interval. So p hat is different, calculations are different. Therefore, CL is different. Okay. Moving on to question E. So here we can see the shift into a probability density function, and we'll just take a read here. So the time taken to reach the top is given by that. So the expected time, so straight away I think another easy 2 marker, it's just finding the expected value of a probability density function. And of course, to do that, you just multiply the function by x, or in this case you multiply by t. So you take the integral of over its maximal domain, so it's infinity to 0 in this case, 0t times ft dt. And that is just equal to, let me just define, mt is equal to 350 times 350 times t over 50 to the power of 2 times e times e to the negative t on 53. Done. And actually, I don't think this e value is right, because I don't think I can just enter e and then, I don't think I can just enter e and then just have it equal to the actual value e. And I'm not sure how to do it on the calculator. Okay, but you guys, oh wait, I think I just got it. Okay, fixing it here. Oh fuck, okay. Let me just redefine it with the correct value of t. Just give me a moment. Here we go. So, getting my e symbol. So it should be bolded, that's how you know you've gotten the right one. T over 50 cubed. Okay, and now we have the right one, and let me just go back to the question. Okay, so integrating this over, fuck, I don't know how to hide this now. Okay, I'll just do it in this step. So integrating mt over its maximal domain times by t. Oh god, I just deleted my page. I'm sorry guys, just give me a second. Oh, okay, you know what? I'm just gonna do this on the calculator I have here, but you know the picture. Just integrate this times by t over its maximum domain to get you the answer for expected value. Define mt is equal to t over 50 squared times e to the negative t on 50 cubed. Okay, and then, sorry guys, I'm just doing it on my calculator right now. I'll tell you the answer in a sec. And the answer is 44.649 and to 1 decimal place, 44.6. So that's the answer for the expected value. There's not much to it. All you have to be able to do is just, you just have to know the formula for the expected value. Moving on to question F. Students who take less than 15 minutes to get to the top of the hill are categorized as elite. Find the probability that a randomly selected student from Massland is categorized as elite. So I think this is another pretty straightforward one. You're just trying to find the probability that a student will take from 0 to 15 minutes. That should be M of t, my bad. So yeah, just integrate that over its domain again. Over 0 to 15 this time. And in the calculator, I have my OneNote's frozen. Okay. And in the calculator, that gives you 0.0266. So that's the probability that you're going to get an elite student. So moving on to question G. The Year 12 students at Mathsland Secondary College make up 1/7. Of the Year 12 students, 5% are categorized as elite. So instantly for this question, I'm thinking about using a Karnaugh table, because I have, one set variable and I have another set variable, and a student can either be one variable or the other. So in this one variable would be Year 12 students, so 12, and also not 12, because if you have Year 12, you can also have students that are not Year 12. And then I have the students who are elite, so E, not E. Okay, so here it tells me that the Year 12 students make up 1/7 of the total students, so 1/7. And then of the Year 12 students, 5% are categorized as elite. So what that's saying is 5% of the 1/7 are elite. So I'll just times 1/7 by 0.05, which is that. Oh, actually, I'll try and leave that in fraction form so it's easy to work out. 1/140. And then you can work out the thing in between them. That's 13/140. That should be 6/7. And then of course, from this you've also obtained that, because you also need to work out this and this in order to be able to work out these two squares. And since it's not given to you the total number or total percentage of elite students, you're going to have to go back and figure out, where have I already figured out E? Because that's what VCAR likes to do. They want you to go back and actually understand what you're doing and find the value that's missing. So in this case, it'll be here, because this is the probability that a student is characterized as elite. So what that's saying is you have a 0.0266% chance of choosing a student that's elite. And with that probability, you could also say that means that 0.0266% of students are elite. So I would have to put in, and I can't keep this in fractions because it's rounded, and then that is 1 minus 0.266, 0.734. Okay, and then I can find these two squares. So let's just read what the question wants me to find first. Find the probability that a randomly selected non-Year 12 student, so I'm trying to find one that's here, is categorized as elite. And you have to notice the wording. So if it, specifically for this question, because it said that a randomly selected non-year student, it's hinting that it's a given question. So you have to write it out as this. Not Year 12. Because in lots of questions, you're going to have to figure out for yourself, the wording of the question and what differs it, or what differentiates it from being a normal one and from a given probability. But this one here, the thing that gives it away is that that non-Year 12 student coming before the categorization. So I know that he's choosing from only non-Year 12 students, so it's a given. So we know that that is equal to PR E and not 12 over PR not 12. And that's just because we've done our table. Let me finish filling this out. That is equal to 0.01945. So we don't need this because we've already got what we want in our question. E and not 12 is just 0.01945 over PR not 12, which is 6/7. And just in the calculator, it'll look like, or the answer would be here. So that gives you 0.0227 to 4 decimal places. Okay. And now the last question for this exam 2 probability. The lens birdwing butterfly. Oh. Okay, I think I mixed up my questions here, and that actually was from the 2019. Okay, we'll just skip this one because it's confidence intervals. Actually, wait. I will. Okay, so this question I think we can just do on our own without any previous info. So it's telling me that 95% confidence interval calculated to be this, and it wants me to determine the sample size. So I could tell you guys like exactly how to do it, but I want you guys to like develop that own line of reasoning to lead you to finding the sample size. So if I have an unknown, which is n, I need an equation that has n to find the unknown. And the related equation here, I'd think to sample proportions, I'd think to everything involving confidence intervals, and I'd come up with this equation. P hat plus or minus square root P hat 1 minus P hat over n is equal to my confidence interval. And from a question I did before, you know that P hat is in the middle of these two, so you can say that P hat is equal to 0.0234 plus 0.0866 divided by 2. So P hat is equal to 0.055. So you've already figured out P hat, and again, a conceptual understanding is required. So if the middle is 0.055, and either side you're going like one standard deviation, or you're going however many standard deviations for a 95% confidence interval, it's fair to say that this bit is equal to, sorry, there should be a z there, that this bit is equal to however many you went from 0.055 to get this bit. So if there's any questions as to how I did this, please ask me in the chat. So I'm just trying to relate all the things I have. So I figured out P hat because, you know, P hat is in the middle of my confidence interval. And then I figured out what this is. And even if you think about it in terms of the equation, P hat plus or minus something is equal to 0.0866. And that something is here. That something is in our equation. So that means that that something, which is this, is equal to 0.0866 minus the P hat. And that minus the P hat is 0.316. So think about 0.316 as the gap between the sample proportion and the bounds of your confidence interval. And that is given by this bit in the confidence interval calculations. So once you have that, you can, you know, do it pretty easily. So set up the confidence interval. Oh, and by the way, the Z value for a 95% confidence interval is 1.96, and you should have that memorized. But when it tells you when it's not a 95% confidence interval, and you know when it gives you some goofy number like let's say 90%, so the way to get the Z value for a 90% confidence interval is to draw a normal distribution like this, and then lay out. You have 90% in the middle because you know you're 90% confident of your mean being within this range, and these bounds are your Z values. So then it's just a simple inverse normal calculation to determine this. And of course 90% in total, so you have 0.05 on this side, 0.05 on this side. So I'll just do on the calculator inv norm inverse normal 0.05, mean is 0, standard deviation is 1. So that means the Z value for a 90% confidence interval is 1.64. And the same thing applies. Like if you had a 70% confidence interval, 80%, whatever, you'd still do the inverse normal to find the Z value. So from that, okay, going back to our original question. So setting out the equation total. So So again, if that's a bit confusing because I've kind of laid everything together, the z value times by the proportion, and our unknown is n, is equal to the gap we feed out, because we feed out that this represents the gap between the sample proportion and the bounds of the confidence interval. And on the calculator, I'd rearrange, so 0.0318 divided by 1.96 equal to that, square both sides, times, oh shit, okay, sorry, I've actually done it to the power of n. So okay, so like obviously you guys can, you know, lay that out step by step so it's less confusing, but I'm just going to do everything now for the sake of being fast. So that's that times 0.055, so that over n, so then so square both sides, so not fuck, square both sides, that means you have, and then you times that by n, so that n divide that by, so that means when you solve, n is equal to 0. Oh shit. So n is equal to 197.624, and you just round. There's nothing involved with like there's no set rule whether you have to round up or down, so just round to the nearest integer. 198. Okay, now last question. I decided to put in an exam 1 question to represent like some of the harder types of questions that you might get in exam 1 you have to do by hand. So Fred owns a company that produces thousands of pegs each day, randomly selects 41, so that's our n, and finds 8 faulty pegs. So instantly we can see that the proportion is equal to 8 over 41 from our formula, and also just from conceptual understanding, you know, what's the proportion of faulty pegs? You have 8 and 41, it's 8 over 41. So pegs are packed each day in boxes, so the actual proportion, so the population proportion is 1 over 6, and each box holds 12 pegs. Let p hat be the random variable that represents the proportion of faulty pegs in a box. So we're trying to find the probability that p hat is less than 1 over 6 in this sample of 12. And again, instantly when you see this, the thing I was going on and out before, convert this to an x value. Instantly, when you see a proportion question like this that says don't use normal approximation, or in exam 1, because you can't use the normal approximation in exam 1, convert this to an x value. So with a p hat value of 1 over 6, and a population size of 12, what's the actual number of faulty pegs, given that 1 over 6 pegs are faulty? Would anyone in the chat like to say how many pegs are faulty, or what the x value is? Okay, it's taking quite a while for you guys to figure this out, so I'll just bring you back to x equal to p hat times n, which is equal to 12 over 6. So the x value is 2, and you can also just figure that out conceptually, like 1 over 6 pegs are faulty, and out of 12 that means 2 pegs are faulty. So the x value is 2, so that means that you're trying to work out the probability that x is smaller than 2. And then it's just a simple binomial probability question. Obviously you use the formula because you know, you're doing this by hand, you don't have a calculator. And remembering PR x is smaller than 2 for the sake of, you know, just making it easier on us, that is the same as PR x is equal to 0 plus PR x is equal to 1. And setting that all out, that means that the probability is equal to 12, 0, 1 over 6, 0, 5 on 6, 12, plus probability of x equal to 1, 12, 1, 1/6, 1, 5/6, 11. So simplifying that, those both equal to 1. That is 12 ways to pick out 1. So 12 times 1/6 is 2, 5, 6, 11. So you're not done yet. That is correct, but you're still not done because Vika wants you to express it in this form. And, you know, this is just going back to exponential laws. So, and we're trying to find a common factor to take out because it wants something in a bracket. So the common factor here is 5/6 to the 11. Because if you think about it, if you're having 5/6 to the 12, that's essentially just 5/6 times by itself 12 times. So if you have 5/6 times by itself 11 times, it is going to be a factor of 5/6 to the power of 12, because 5/6 times by itself 11 times is just 1 5/6 away from being times 12 times. That means that 5/6 to the 11, you can take that out as a common factor. You'd be left with 5/6 on the inside to the power of 1, which is just 5/6 plus 2. So that's 5/6 to the 11 times 5/6 plus 2, and you can simplify that to zoom in a bit more. Simplify that to times 17/6. So that's your answer. 17/6 to the power of 5/6 to the 11, the way that Vika wants. So that is everything for probability. That that was just me covering a few questions that I thought would be very useful to go through. So reiterating, you need to know how to do the different types of probability. Probability density function, binomial distribution, and normal distribution. And the key thing for sample proportions, which I think is one of the most confusing aspects of probability methods, whenever you see something like, let me just draw this. Whenever you see something like, convert this to an x value and then use the binomial distribution to solve, that'll make your life, I think, if you think about it that way, it'll make it a lot less confusing. So yeah, just again, whenever you see something like this, proportion is bigger than a number, convert to an x value and then solve using the binomial distribution. And obviously also remember that calculator trick I taught you. It's not in this, but if you guys want a refresher to like put in your band reference, I'll be uploading this to YouTube, so everything's good. So that's all for today. Thank you for listening, guys. Doing this helps me to revise as well, going through some nice probability questions, and I hope this helps you guys a lot. So I'm gonna end the stream. See you guys later.